Hi, in this video, we're going to be working on integrals as net change. So it's times where when we do that antiderivative, we're not necessarily going to just straight dive into that antiderivative. We might need to do some fancy stuff. So if you see a question asking for things like displacement or its final position or what's going to happen when it's all done, that is going to be just regular integration stuff. But if it's looking for a total distance traveled versus our total area, that is going to require this integration of an absolute value. You can see the difference of it in this example here. So this particle's displacement is where it is after it has been running around doing all of its velocity stuff. Since it had a lot of negativity, it is gone to the left. So its final position is 1.44 whatever's to the left. However, if we talk about the total distance that it moved, since it was moving forward and backwards, we get this other value. We get a much larger distance that it overall traveled, that 1.939. So we'll be looking for this idea of when the particle is moving to the right and when moving to the left. So it has been moving a lot, but you could say that these two directions have almost undone each other. So it's gone almost nowhere. And same thing with these two. And depending upon the problem, sometimes we want just where it's going to be at when we're done. And other times we only care about like how far has it moved. So let's try it with that. This one is looking for the particle's displacement. So that's telling us we want to know where it is ending at. So we don't care that it's wobbling up and down. We just want to do a regular integration of this thing. So let's do that. We want the integral. Oh, pen, please. From 0 to 2 pi of 5 sine squared t cosine t. I don't care that it's going up and down. I don't need to add an absolute value because it's looking for displacement. I just do regular integration. In order to integrate this thing, I am going to need to do a u substitution. So I see my innermost piece as being sine of t. So I'm going to have u equals sine t. And that has a wonderful consequence of du being derivative of sine is cosine t dt. Oh, oops, I didn't write a dt up there. There we go. So when I substitute that in, I get the integral from 0 to 2 pi. That 5 is just going to chill there. Well, we can even chuck it out front because we don't really need it. And we get u squared. And this cosine t dt gets replaced with just a du. So this integral is going to be 5 going from, well, u cubed over 3, going from 0 to 2 pi. Bring back my sign, so we get 5 from sine cubed t over 3, going from 0 to 2 pi. We do our top minus bottom. So the top, sine cubed, our top is 2 pi over 3 minus the sine cubed of 0 over 3. All right. So that is going to be 5. The sine of 2 pi is 0, so that is 0 over 3. What? And that's got to have a cubed on it, minus the sine of 0, which is also 0. Oh, why did I write sine? Sine of 0, which is also 0, so that's 0 cubed over 3. So after all that wiggling around, this thing has gone nowhere. So it's 5 times 0, which is 0. So it has a displacement of 0. That's our displacement. ENT, displacement. But this question was asking, what is the particle's final position? Since it started at 3, it's kind of wiggled around, it's gone forward and backwards, but its final resting spot is going to be at a displacement of 0. So it's gone nowhere from 3. So the particle's final position is 3. So we can write that out. Since the displacement is 0, the final position of the particle is 3. Done. For part C, we want to find the total distance traveled by the particle. So what we need to do is we need to include that absolute value. So the time that it is moving to the left, we still count that as moving forward. So we actually can get the distance. Then they're not going to cancel each other out, having a positive and a negative value. So we don't know how to do the antiderivative of an absolute value. Plus, we don't even really need to. What we want to do is we just want to break this up into different pieces. We'll have this positive piece. Oh, hey, come on, give me a pen here. We want this positive piece for which we won't have to do anything. But then when it goes negative right here, we just want to slap a negative in front of it because that negative and the other negative for being under the axis will cancel each other out and it'll just be positive. And then we'll have this final piece where we don't have to do anything because it's already above. So we're going to do the antiderivative from 0 to this spot right here, pi over 2 of our 5 sine squared t cosine of t dt. Then we're going to add that to another one. This purple one is going to be the antiderivative. This is going to go from pi over 2, and it's going to end right here at 3 pi over 2. And it's still going to be that 5 sine squared t cosine of t dt. But we want this thing to be positive and not negative. Well, that's easy fix. You just slap a negative in front of it. Done. Then we're going to add that to this final chunk right here, which is just going to be normal. So it's just going to be 3 pi over 2 to 2 pi. And we'll do positive 5 sine squared t cosine t dt. I don't know why I put parentheses around that first one, but I didn't do it for all the other ones. Now, all of those integrations are going to follow the same pattern of integration as we did before. So we'll substitute a u of sine t. We'll do our dt stuff. So all of our integrals are going to be the same thing. You can check what we did in part B, but all of our integrals are going to be identical. So I'm just going to save myself a little bit of trouble and just kind of do the same thing over and over and just jump right to the end. So it'll be 5 sine cubed of t 3. Our first one is going from 0 to pi over 2. Then we'll have a purple one in the middle. That'll be minus 5 sine cubed of t over 3, going from pi over 2 to 3 pi over 2, plus our final piece of 5 sine. Why can't I write the sine? Sine cubed t over 3, going from 3 pi over 2 to 2 pi. All right, so we just got to evaluate each one of those. So when we do the red one, our top minus our bottom, when we put in that pi over 2, the sine of pi over 2 is 1. So we just get 1, so that's 5/3. Minus our bottom, the sine of 0 is 0, so that's not going to subtract anything. So I'm not going to do the bottom part. Then we get minus the sine of 3 pi over 2 is negative 1. So that'll be a negative 5/3. And minus our bottom, the sine of pi over 2 is 1. So that'll be 5/3. Our final part, the blue part, we do the top, which you can't see because I'm in the way, but it's 2 pi for our top. The sine of 2 pi is 0. Yeah, sine of 2 pi is 0. So that is just 0 minus the bottom, which is negative 5 pi over 3, because we just did that. 5 over 3. Okay. So this ends up equaling 5 thirds. This is negative 10 thirds, but then it becomes positive, so it'll be positive 10 thirds. And then this minus minus will become a positive, so we get another 5 thirds. So our total distance traveled is 20 thirds. Yeah, total distance traveled. Total distance traveled of the particle is 20 thirds. And that's done. All right. In this example, I've already taken the time to just figure out what the area of our different shapes are. We want to figure out where the particle is at the end of the trip. So negatives are going to be negatives and positives are always positive. But we want to figure out, okay, well, it was going backwards and then it went forward and then it was going backwards again. So the total amount of that it has moved, its displacement is 3. So it has a displacement of 3. Because we're doing that -1 plus 5 plus -1. We have a displacement of 3 since it started at 2. Its final position at the end of the trip, its final position is whatever 3 plus 2 is, which is 5. To find the total distance traveled by the particle, we need to say, hey, when you're negative, that still counts as being positive. So these two places where it had a negative value for the antiderivative, we got a negative value here. We want to just make those two things positive. So the total distance traveled is 1 plus 5. So our total distance traveled is 1 plus 5, which is 7, because we're doing the absolute value of those things for our total distance traveled. Because even though that these two directions kind of undo each other, we want to count them both. And that's it for integrals as net change. A reminder of the things that you're looking for is displacement, final position, or at the end of the trip is talking about just a regular integration. We might get a little more complicated if we see total distance traveled or total area, kind of that total thing. We want to find the absolute value of our function and then integrate, which might mean breaking it up into a couple different pieces. But if everything is staying positive, we don't have to worry about anything too fancy. And that's it. Thank you for watching. So long.